let's look to see about the effects of the power functions. In your last videos, we defined the power functions and we looked at the sketches of the power functions given the integer powers, whether they were even or odd. So let's review what we have already learned. So if f of x equals x to the n and n is even, then we know that the function will take on a shape similar to this. And what we know about that is the end behavior. And so as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, f of x still goes to infinity. In other words, as we go out in either direction, the function goes up. Okay, and that's true if n is even. Now, if we take in this situation f of x equals the negative of x sub n, x to the n, where n is even, well, we know that that is a reflection of x to the n about the x-axis. So it'll look like this. It'll have the same general shape except my end behavior changes. And so this time, as x goes to positive infinity, f of x goes down, so towards negative infinity. And as x goes to negative infinity, f of x still goes down. So my end behavior flips. Okay? Now what happens if n is odd? Well, we know the general shape this takes on if n is odd. And it'll look kind of like this. Okay, and so we know that as x goes to positive infinity, so out towards the right, f of x blows up, so it goes to positive infinity. As x goes to negative infinity, f of x also goes to negative infinity. So as I go this way, my function goes up. As I go this way, my function goes down. All right, and this is what my power functions look like if n is odd. And so what do we think will happen if we reflect this one? So if I want to now look at f of x equals the negative of x to the n where n is odd, well, we know it's a reflection of this one about the x-axis, so it should look like that. And again, this changes my end behavior. As x goes to positive infinity, this time f of x goes towards negative infinity. As x goes to negative infinity, this time f of x goes to positive infinity. So as I go out this way, my function operates in that behavior. Okay, now we want to see what happens when we combine a bunch of power functions together. So let's review again what a polynomial in standard form looks like. This is just our notation, which can be a bit cumbersome, but this really means that I'm writing my polynomial in descending powers. So x to the n, then a power less, then a power less, then a power less, all the way down to, this is really x to the 0, which is the same thing as 1. Now, my coefficients can be 0, which means I might not have one of my x terms. The only requirement is that a sub n is not 0. And if that's the case, then I have an nth degree polynomial. Okay, it's the highest degree that is present. It's the highest power that is present, and that determines my degree. In standard form, we always write that power in descending order. Okay, and here is something that is fascinating. As we go out far enough, so as x goes towards infinity, so now I'm describing end behavior, these terms that sit below the lead term have less and less of an impact. And so the end behavior of my polynomial is determined, polynomial, let me spell that correctly, is determined by the lead term. By the lead term, or the highest power present. So that's only if you've written it in standard form. So my highest degreed term, the highest exponent term, which determines my degree, also determines the end behavior. It's determined entirely by this lead term. So let's look at some examples and see how we would answer them. All right, if we look at this first example, first thing we should check is, are we in standard form? And we are. I've written my powers in descending order. And so then I can circle my lead term, which is x to the 5th. So first of all, if I asked you what the degree is, you would tell me the degree is 5, because that's determined by the highest power. And the end behavior is determined by this lead term. And we already know this is an odd degree polynomial with a positive coefficient, so its end behavior should look like this. And how would we talk about that? As x goes to infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. Okay, let's look at example 2. Is it in standard form? 4th, 1, 0. Yes, it is. It's written in descending power. I'll circle my lead term, which determines my degree. So my degree here is 4. And my end behavior is determined by the behavior of negative x to the 4th. Now, this is an even degree power function with a negative coefficient. So we know the end behavior looks like this. All right, let's look at the next example. X to the 10th, 9th, 8th, 7th, 6th, 1, 0. I am in standard form, so I need to look only at that first term. The degree of this polynomial is 10, and the end behavior is determined by x to the 10th, which is an even degree power function with a positive coefficient, which means its end behavior looks like this. In my last example, x cubed minus x to the 5th plus 1, if I'm not careful, I might start talking about the end behavior being determined by x cubed because it appears first, but you would be incorrect. I'm not in standard form. This can be rewritten as minus x to the 5th plus x cubed plus 1. I'm now in standard form. This is my lead term. The degree of this polynomial is 5. And the end behavior is determined by this power function, which is an odd degree with a negative coefficient, which means my end behavior looks like this. Okay, let's now look at how different power functions compare to each other. So let's try to sketch x squared and x cubed on the same graph for x bigger than or equal to 0. That means we're going to ignore this side of the graph. All right, and we know the general shape of x squared and we know the general shape of x cubed, but we might not know how they sit relative to each other. So let's do what any good mathematician should do and plot some points. We plug in 0, we get 0, we get 0. So on both graphs, 0, 0 is on both graphs. I plug in 1, 1, 1. So 1, 1, I'll put it right up here, is on our graphs. What about 1/2? Well, if I square it, I get 1/4, but if I cube it, I get 1/8. So notice 1/8 sits below 1/4. Let's do another. 1/4, if I square it, I get 1/16, and if I cube it, I get 1/64. So again, x cubed sits below 1/16. Now, this should give you a general idea of what's happening between 0 and 1. When I square the number, I get smaller, and when I cube it, I get even smaller. So if I were to graph x squared, I might think it looks like this to the right, and my x cubed is going to sit below it. Okay, it sits below it. But what happens if we get past 1? So for example, if I put 2 in there, well, 2 squared is 4, 2 cubed is 8. And it's quick to see that once we're past 1, cubing it will make my function bigger than squaring it, so it starts to sit above it. And again, we all know my drawing techniques. This is the general shape of it, although it curves out better that way. But this is how my x squared compares with x to the 3rd. What do you think would happen to x to the 4th? Where would it sit?